This is, of course, a great day for physics at Princeton, and actually a great day to be chair of physics at Princeton. And it's also a well-deserved recognition for a truly great scientist and colleagues, and it's hard to imagine a more well-deserved prize and a more gracious recipient. Jim, he's one of the true pioneers, one of the founding fathers of a whole branch of physics, now called theoretical cosmology, the field that led to the discovery and study of the Big Bang and the early history of our universe. Jim became a theoretical cosmologist long before it was popular, long before it was considered a serious quantitative branch of physics. When Jim entered the field, cosmology and more generally the study of Einstein's theory of general relativity was still in its infancy. Einstein's theory had been tested at the scale of our solar system, but its profound predictions about the history of our universe was not yet well developed and considered beyond the limits, and at the time was considered to be beyond the limits of our observations. Jim's work laid the foundations for almost all of modern investigations in cosmology and transformed physical cosmology from a highly speculative field into a respectable quantitative branch of physics, and one of the most successful scientific endeavors of this day, with new discoveries every year. With Bob Dickey and others, he predicted the cosmic microwave background, the visible signature of the Big Bang. He made major contributions to Big Bang nucleosynthesis, the process by which elements get formed during and after the Big Bang. He contributed to establishing the problem of dark matter and dark energy, and was the leading pioneer in the theory of cosmic structure formation in the 1970s. In the early 1980s, these three ideas pioneered by Jim gave rise to the formation of what is now called the standard Big Bang model of cosmology. So whenever someone wins a Nobel Prize, there are usually various institutions and universities that claim and that will say, he or she is ours. In this case, Jim is really ours. We're not sharing him with any others, except perhaps with Manitoba. He is a member of the Order of Manitoba.
Thank you.
And he, indeed, as Chris said, he left Manitoba in 1958 to complete his doctorate with Rob Dickey, and he stayed here since then. For my personal perspective, indeed, I got to know Jim first as a name on a book that I would see many, many times. As was mentioned, Jim has written several books that became standard references in the field. The book on physical cosmology is really a marvel in depth and insight, way ahead of its time. And it's also written in brilliantly lucid prose and with balanced views of what it means to discover new things in physics and cosmology. So when I came to Princeton, certainly someone who was first a name became a person that you could have conversations with and that you could learn very valuable things from. It's always a joy and a privilege to hear Jim give a lecture or a talk, or to talk with him about big questions that are still puzzling us today. It's also a pleasure to have Jim in a lecture, because he's always the one who asks the deepest questions to the speaker, and questions that usually illuminate the entire context of the lecture. As one of his colleagues, Suzanne Staggs, wrote, Jim has the remarkable ability to look at the big picture, which of course is a very useful skill if you look at the whole universe. But Jim, so as Suzanne wrote, holds in his head the entire scope and grandeur of our universe, but is also able to drill down to its fine details and describe them and interpret them. Gracious and generous to his students and his colleagues, and as an illustration of his modesty, during the celebration this morning in the physics department, Jim expressed actually disappointment that the theory that he developed in the early 80s turned out to work so well. It's being confirmed by experiment after experiment, but scientists of Jim's integrity recognize that in spite of all the progress, there are still more questions than answers. People like Jim are more interested in the progress of knowledge than in their own fame, sometimes to the point where indeed they prefer to be proven wrong than to be proven right. But today is a day where, Jim, you should be proud for being proven right. Scientists like of Jim's stature and impact are a very rare breed. He has truly contributed to our understanding of the universe in profound ways, and we are very proud to have him as our colleagues. Congratulations. Jim.
Thank you. Herman, I am proud. I'm really delighted, proud and delighted at the friendly reception I receive here, at the lining up of people when I arrived at the building in physics this morning. Just such a joy to see the recognition of work that so many have done that is so fascinating. I guess the best thing I can do is to tell you the story of my life in short. I arrived at the University of Manitoba with only a vague notion of what I wanted to do. I'm deeply indebted to the Department of Physics and its faculty and fellow students for showing me that I love physics. I'm in particular indebted to Ken Standing, a professor of physics there, about 10 years my senior, who had been a graduate student here at Princeton. He said, "You will go to Princeton for graduate study." It was not an advice, it was, "You will go." I had the great delight of seeing him just a couple of years ago. He had a great career in the University of Manitoba. I arrived here with dreams of doing particle theory. To my intense great fortune, I got diverted by the presence, the inspiration of Bob Dickey, Professor Robert Henry Dickey. The department is such a treasure trove of people who are doing wonderful things. He, a brilliant experimentalist, came out of the World War II, war research on radar and the like. He spent 10 years here at Princeton doing laboratory physics in what you might call quantum optics. Then he decided that gravity physics is too important not to be explored further than the old classical experiments. I arrived in 1958. He already had a large group going, doing research in gravity physics. Gravity operates on the scale of planets, so we studied them. It operates on the scale of galaxies. It operates on the scale of the universe. That's how we got into cosmology. That gravity research group, I'm so delighted to say, is still in operation, richly active, and by my count, in its fourth generation. When I started doing work in cosmology, on the advice of Bob Dickey, 1964, the subject was, I should emphasize, the subject was a real physical science. It had a theories, it had observations, it had work in progress to try to bring the two together, but the rate of progress was so minuscule and slow. That made me very reluctant to get into cosmology. Such a chancy subject. But I discovered, to my great pleasure, that because there are very few people working in the subject, I could, just without consulting the literature, do interesting things and be pretty sure no one else was doing them. Such a change from today. And as I did research, I saw new things to think about that led to new things. And, I stopped 55 years later. I find it amazing always to consider that nature operates by rules that we can discover. I'm particularly and intensely amazed to consider that when I worked in this field, we had a theory of gravity, general relativity, which passed one demanding test on the scale of the solar system. In cosmology, we're invited to apply that same theory, extrapolated to scales that are about 10 to the 15 times larger. Spectacular. Why in the world should you assume that the same physics would apply on those scales as in the solar system? I was nervous about that. I was nervous about the lack of evidence about the nature of the universe. But the evidence kept appearing. It was quite a joyride. I remember well, 1982, I introduced a theory that went by the name of CDM, cold dark matter. I made it up out of whole cloth to fit the observations we had at the time. 2 years later, I added lambda, Einstein's cosmological constant. It became the theory that's now very firmly established. But in 1984, when I put together that theory, I was very unhappy with the fact that it grabbed a lot of attention. Why are you concentrating on this particular theory? I could make a dozen others up that would fit the data equally well. This was the simplest possibility, but by no means the only one. I spent much of the late 80s, early 90s inventing other theories just because I felt that we shouldn't be so confident about the one theory. But I was totally wrong. The theory survives to my deep amazement, and as Herman remarked, slightly to my regret, because we can be very sure that theory isn't the final answer. And we can be very sure that as we discover new aspects of the expanding and evolving universe, we will be startled and amazed once again. I hope you guys hurry up to make those discoveries so I can enjoy them. I don't think you can imagine how good this makes me feel.
Thank you. Thank you very much, Professor, and thank you, President Eichgruber and Professor Verlinde. This is the point at which we test that premise of there being more questions than answers as we forward research into the universe, but try to balance that equation. There are microphones in the audience. If you have questions, please raise your hand. While we search for those hands, if I could kick us off with a question that came from some of our media friends from the North. Professor Peebles, you grew up in Winnipeg and on the prairies of Manitoba. Do you recall how your interest in the stars and galaxies took hold? What sparked your interest in science that has brought you to this day?
So first, I must, a slight correction. I was born in St. Boniface, the Francophone sister city of Winnipeg.
Duly noted.
I grew up in Norwood and then St. Vital, small municipalities just south of Winnipeg. What was the other part of the question? Well, why? I have always, since one of my early memories is throwing a tantrum because I wasn't allowed to put together the coffee percolator. I remember as a very young child, but I could read, looking into one of my sister's textbooks and seeing an explanation of a compound pulley. I thought that was really neat, and I still do. My father was handy with his hands, and I certainly enjoyed working with him. I loved building things. I was never very good at it, but I always loved doing things with my hands. I simply like looking at the world around us and seeing, if possible, I might mention that clocks in our house were always at hazard. I loved to take things apart, couldn't get them back together. I love things, the way things work. Just, we are all built in different ways, and that's my build.
Brilliant, thank you. Questions?
Professor Chris Tolley from the physics department. Jim, what did it feel like when the first fossils of the early universe were discovered? And what other relics from the early universe would you like to see one day measured?
Right. So you must understand when the radiation was discovered, it was seen to be more or less isotropic, the same in every direction. That's all you knew. The press got excited. This is radiation from the early universe. What do you mean? It could be anything within limits. The evidence that is really from the early universe took 25 years. It wasn't until two crucial experiments, 1990, wasn't it? Showed that the spectrum is just that of thermal radiation, as you would expect from a hot Big Bang. I might mention that that experiment was done brilliantly well by two groups independently, each of which took 15 years to get the experiment done. One group, NASA, was led here at Princeton by my deep friend and colleague, David Wilkinson. A magnificent experiment, although the project was led by him. John Mather was the person, the PI in charge of that investigation. In Western Canada, University of British Columbia, Herb Gush was doing the same experiment independently. So moving to consider that they got the answer, it's thermal, within months of each other after 15 years' work. Wow. Again, what would I like to see now? Well, of course, there's that, the dark matter. Though not all agree, I think it's very clear. The dark matter is there. The evidence is so strong, well-checked, well cross-checked, so consistent. So yes, there is a mysterious form of matter. We call it dark matter for better, well, it's just a word. We have a few constraints on its properties. We're dying to know what it might be. There are experiments in progress that are working very hard to find it, to detect it. It's really a tough game because since we don't know what it is, we don't know where to look. And so these experiments each must choose a direction, plow hard, work the devil out of it, and you don't know if you're looking in the right place. It will show up. They always do, so it will happen. I warn you that the first announcement of detection will be greeted with great joy. This is the microwave, this is the dark matter. But we won't know whether that's really the dominant dark matter or just a trace element. My bet is that the dark matter is complicated and that the discovery will be a process of winnowing out different candidates, some that are all there but in varying amounts. It'll be very exciting. What we do about Einstein's cosmological constant is much deeper. It's totally enigmatic. It's a term that Einstein recognized is allowed by his theory. He threw it in and then in disgust threw it out again. And that's the story I was advised when I was a student, a graduate student and then a postdoc. It's back, and it is so enigmatic. Someday we will sort it out. You all will sort it out. There are wonderful prizes to be, discoveries to be made. Of course, the room is full of people who are on to wonderful discoveries. Science marches on in many directions. I don't think there is a final theory of anything. It's theories all the way down.
Another question.
Professor David Spergel from our astrophysics department.
What observation most surprised you in the development of cosmology?
Sorry?
What observation most surprised you in the development of cosmology?
Well, the present state of affairs is a total surprise. No, I can't name any specific problem, specific discovery, because you see, it's a process. Well, for example, we have the thermal radiation left over from the hot early universe. First detected, in early experiments with microwave communication as unwanted noise. Seen to be present, clearly, seen to be smoothly distributed across the sky to a good approximation. A little hard to imagine how it could be produced by sources in the universe as it is now, but the universe is capable of surprising us, and it has before, will again, but that proved wrong. It was indeed a moving moment when we first learned that the spectrum is close to thermal, meaning it surely is a remnant from the hot early universe. I remember David Wilkinson drawing me aside as if he had a dirty postcard and showing me the data ahead of time. That was a memorable moment. David, I hope you won't mind my telling everyone that when you were in my course, you and your happy fellows wrote down all of my jokes.